Every day, the world consumes approximately 100 million barrels of oil. This black gold powers our vehicles, heats our homes, and serves as the raw material for countless products we use daily. But how does crude oil transform from a geological formation deep underground into the gasoline that fuels our cars? This journey involves sophisticated engineering, massive infrastructure, and complex chemical processes that span from remote oil fields to modern refineries. Part 1: Finding the Oil, Exploration. The journey begins with exploration. Geologists search for oil using a combination of satellite imagery, geological surveys, and seismic technology. Seismic surveys are particularly crucial. They work by sending shock waves into the earth and measuring how they bounce back. Different rock layers reflect these waves differently, allowing geologists to create detailed underground maps and identify potential oil reservoirs. Oil forms over millions of years from the remains of ancient marine organisms that settled on ocean floors. Heat and pressure transform this organic material into hydrocarbons, which migrate through porous rock until they become trapped beneath impermeable layers, creating oil reservoirs. Finding these reservoirs requires analyzing geological formations that typically existed 100 to 300 million years ago. Once a promising site is identified, exploratory drilling confirms the presence of oil and determines whether extraction is economically viable. This initial phase can take years and cost hundreds of millions of dollars before a single barrel is produced. Part 2: Extraction, bringing oil to the surface. When a viable oil field is confirmed, extraction begins. There are two main types of oil extraction, onshore and offshore, each with unique challenges. Onshore drilling involves constructing drilling rigs on land. The drill bit, often made of industrial diamonds or tungsten carbide, penetrates through thousands of feet of rock. As drilling progresses, steel casing is installed to prevent the well from collapsing and to protect groundwater from contamination. Modern wells can extend horizontally for miles, allowing a single drilling pad to access oil from a vast area underground. Offshore drilling is even more complex. Platforms must withstand harsh ocean conditions while drilling through both water and seabed. Some platforms float on the surface, while others stand on legs anchored to the ocean floor. In ultra-deep waters, drilling can occur at depths exceeding 10,000 feet below sea level, requiring extraordinary engineering precision. Initially, oil flows naturally due to underground pressure. This is called primary recovery. As reservoir pressure decreases, secondary recovery methods inject water or gas to maintain pressure and push more oil toward the wells. Eventually, enhanced oil recovery techniques, such as injecting steam or chemicals, help extract additional oil from depleted reservoirs. These advanced methods can recover up to 60% of the oil in a reservoir, compared to just 10% with primary recovery alone. A single offshore platform can produce hundreds of thousands of barrels per day. The extracted crude oil is typically a mixture of hydrocarbons, water, sand, and gases, which must be partially separated at the extraction site before transportation. Part 3: Transportation, moving the crude. Once extracted, crude oil must travel from remote locations to refineries. This logistical challenge involves multiple transportation methods. Pipelines are the most efficient method for large volumes. The United States alone has over 200,000 miles of oil pipelines crisscrossing the country. These pipelines use pump stations every 50 to 100 miles to maintain pressure and keep oil flowing at speeds of 3 to 8 miles per hour. Modern pipelines include sophisticated leak detection systems and can transport different types of crude oil sequentially, separated by special cleaning devices called pigs. Oil tankers transport crude across oceans. The largest supertankers can carry over 2 million barrels of oil, that's roughly 84 million gallons. These massive vessels feature double hulls for safety and segregated tanks to carry different crude grades. A typical journey from the Middle East to the United States takes approximately 3 weeks. Rail and truck transport handle smaller volumes or serve areas without pipeline access. While more expensive per barrel, these methods offer flexibility for reaching refineries in remote locations. Throughout transportation, crude oil is carefully tracked and sampled. Different crude oils have different properties, some are light and sweet, low sulfur content, while others are heavy and sour, high sulfur content. These characteristics determine which refineries can process them and what products they'll yield. Part 4, the refinery, transformation begins. Refineries are vast industrial complexes where crude oil undergoes transformation into usable products. A modern refinery can process 200,000 to 500,000 barrels daily and operates 24/7 for maximum efficiency. The refining process begins with distillation. Crude oil enters a towering structure called a distillation column, which can stand 150 feet tall. The oil is heated to approximately 750 degrees Fahrenheit, causing it to vaporize. Inside the column, these vapors rise and cool at different heights. Different hydrocarbon molecules have different boiling points, so they condense at specific levels. At the top, the lightest products condense, gases like propane and butane. Moving down the column, we find gasoline-range hydrocarbons, then kerosene and diesel fuels. Near the bottom, heavier products like lubricating oils form, while the very heaviest materials, such as asphalt, remain at the base. This initial distillation produces only about 40% gasoline from typical crude oil, but refineries need to produce closer to 50% gasoline to meet market demand. This is where conversion processes become crucial. Part 5, cracking and conversion. Catalytic cracking breaks large, heavy hydrocarbon molecules into smaller, more valuable ones. In this process, heavy oils are vaporized and passed over a catalyst, typically a fine powder of zeolite mixed with other materials, at temperatures around 900 to 1000 degrees Fahrenheit. The catalyst facilitates chemical reactions that split long-chain hydrocarbons into shorter chains suitable for gasoline and diesel. Hydrocracking uses hydrogen gas under high pressure and temperature, along with catalysts, to break down heavy molecules while simultaneously removing sulfur, nitrogen, and other impurities. This process is particularly important for producing clean-burning fuels that meet modern environmental standards. Alkylation and reforming processes rearrange molecular structures to create high-octane gasoline components. Alkylation combines small molecules into larger, branched hydrocarbons ideal for gasoline. Catalytic reforming converts low-octane components into aromatics and other high-octane compounds, significantly improving gasoline quality. These conversion processes are what allow refineries to customize their output based on market demand, producing more gasoline in summer when driving increases or more heating oil in winter. Part 6, treatment and blending. Before products leave the refinery, they undergo extensive treatment to meet environmental and performance standards. Hydrotreating removes sulfur, nitrogen, and metal contaminants. This process is essential for producing ultra-low sulfur diesel and gasoline, which emit fewer harmful pollutants. The hydrodesulfurization process alone represents a major portion of refinery operating costs but is crucial for environmental protection. Modern gasoline isn't a single product but a carefully engineered blend. Refiners combine various streams from different processes to achieve specific properties: the right octane rating, appropriate vapor pressure for the season, and precise chemical composition to minimize emissions. Additives are incorporated to prevent engine deposits, reduce corrosion, and improve performance. Different seasons and regions require different gasoline blends. Summer gasoline has lower vapor pressure to reduce evaporative emissions in hot weather, while winter blends vaporize more easily for better cold weather starting. California and other regions require special formulations to meet strict air quality standards. Part 7, Quality Control and Storage. Throughout the refining process, extensive quality control ensures products meet specifications. Samples are continuously tested for properties like octane rating, sulfur content, vapor pressure, and dozens of other characteristics. Modern refineries use automated systems that can adjust processes in real time to maintain product quality. Finished products are stored in massive tank farms surrounding refineries. These tanks, some capable of holding millions of gallons, provide buffer storage that allows refineries to operate continuously while managing varying supply and demand. The tanks are color-coded and clearly marked, with sophisticated inventory management systems tracking every gallon. Part 8. Distribution to consumers. From the refinery, gasoline begins its final journey to your local gas station. It travels through product pipelines specifically designated for refined products, separate from crude oil pipelines. These multi-product pipelines can carry gasoline, diesel, and jet fuel in batches, one after another. At distribution terminals near population centers, gasoline is loaded into tank trucks. These familiar vehicles deliver fuel to individual gas stations, typically carrying 8,000 to 11,000 gallons per trip. The driver connects to underground storage tanks and carefully monitors the transfer.